These are two typical examples of case 3. Here, the power is non-real. There, the power is irrational. For both, we use this definition. And by replacing log z by ln of absolute z plus I, argument of z, we get this for z to the alpha. Now, in the irrational case, this argument would have infinitely many values. That's the argument of z to the alpha. That's why z to the alpha has infinitely many values. In the non-real case, the imaginary part of alpha times the argument of z would be a part of the real part of the exponent, because I times I is -1, is real. And that decides the absolute value of z to the alpha. So in that case, there are infinitely many absolute values. So once again, when alpha is irrational, there are infinitely many arguments. When alpha is non-real, there are infinitely many absolute values. Therefore, in either case, z to the alpha has infinitely many values. Now let's look at all three cases. Z to the n, when n is an integer but not 0, is single valued. Z to the p over q, where p over q is a rational number but not an integer, and p and q are relatively prime, there are exactly q values, and they're all different. In the remaining case, there are infinitely many values.